Okay, hello to everyone. I'm here to represent the GIADA team and to talk to you about the GIADA instrument, which is on board Rosetta with the main aim to characterize the dust environments, in particular the physical properties of the dust grains. Let's have a look to how the instrument works. The instrument is made of 3 subsystems. You see on the left side, there is the prototype model we have in our lab for calibration issues, and then a scheme of how the subsystem are settled, and then on the right, the GIADA mounted on board Rosetta. So the first subsystem is the grain detection system. It's a laser curtain which detects the dust grains as they pass through the laser curtain, and it provides data on the grain speed and the cross-section of the dust crossing the laser curtain. Then the impact sensor, which is yes, so this is the laser curtain. This is the entrance where the dust grain get into GIADA. And then here you have the impact sensor, and the impact sensor is devoted to the measurement of the grain momentum, which is determined by the impact of the grain on an aluminum plate. Underneath there are 5 piezoelectric sensors. And then there is the microbalance system. These are 5 microbalances, which are just here, just in the around the entrance of GIADA, and they look at different direction in space, and they are devoted to the measure of cumulative flags, dust flags for grains which are smaller than 10 microns. Let's have a look to the ranges of measurements. These are the quantities that GIADA measure directly, so the speed of each grain, which ranges from 0.3 meter per second to 300 meter per second. And then the momentum, you see this is the range that we can measure with the impact sensor, and then the fluence of the dust particles by the microbalances. Then, from this measurement, we actually can derive, you see here, we measure the speed and we measure the momentum, so we can get the mass of each single grain. Then we can get the flux of the dust grains coming on depositing on the microbalances. And then here, there are quantities that can be derived by the GIADA measurement. So the grain diameter, this is derived by the measurement of the geometrical cross-section that is performed by the laser when the grain enter into GIADA. It passes through the laser curtain, and this measures the geometrical cross-section of each grain. But this, of course, depends on the optical properties. The ranges of the size of the grains depends on the optical properties of the grains. In fact, for high albedo, we can measure from 30 micron to 200 micron. This is as a reference. I put the material that we use in the laboratory for calibration curves. And then for low albedo, so let's say amorphous carbon, we can get measures for grains from 150 to 800 micron. And then from these measurements, of course, we measure the size of the grain, we measure the mass of the grain, so we can get hints also on the density of each grain. In this case, it's not a real measure, it's an estimate. It's like constraining the range of the bulk density of each grain. I will speak from now on of this type of detection for GIADA, GDS only. This means that they are detected only by the laser curtain, even if they are passing through. Maybe because of the low momentum, lower than the sensitivity of the impact sensor, they are detected just by the laser curtain. Then the impact sensor only, they can be detected also only by the impact sensor, maybe because they are too small to be detected and from the laser curtain. And then some of the grains are detected by both subsystem, so this would be GDS plus IS. So what did GIADA see? So the early detection, the first detection was recorded at about 800 kilometers from the nucleus, when the nucleus was still at 3.7 AU from the sun. And so it was here, and then approaching the comet, other 3 detections were recorded. Then the spacecraft started the pyramidal trajectories, first at about 90 kilometers from the nucleus, and here we detected 9 grains, and then another 40 grains when we were at 60 kilometers from the nucleus. These are the very first detections, but now there are much more. GIADA detected till now, from the 1st of August till the 11th of December, 800 grains. And as I said, among these 800, some are just GDS detected. And in fact, this selection is helping us in classifying different types of particles. Let's say that this GDS only, they are very numerous. In fact, you can see that they are 700, and just 70 and 70 are the impact sensor only in the GDS plus ES. These are very much, and they come into GIADA like clouds of particles. They come in about 10 seconds, like more than 100 grains, and they are very close in time, one to the other. And we interpret these grains, we tend to interpret these grains as fluffy particles that maybe are broken from just before entering GIADA. We are looking into this, looking for also some maybe electric explanation of causing this fragmentation of the grains. And then the impact sensor only, these are 70, and the ratio between the impact sensor only and the GDS only, it's changed from the very beginning till now. In fact, at the beginning, they were just 1/10 of the GDS only, and this is now, while during the early detection, so let's say August, early September, we got 3 times more the impact sensor detection than GDS detection. So this can suggest the presence now of a different type of particle, like bigger or brighter, because the GDS is able to look at them, to see them, to detect them, and maybe they are less dense and they do not have a high momentum enough to be detected by the impact sensor. And that's from these grains, GDS plus IS. This detection allow us to measure the velocity of each grain, and the velocity is ranging from 0.3 meters per second to 12 meters per second. And this detection allowed us also, of course, to derive the mass, the velocity, the momentum, and also to constrain the range of density of these grains. We are now studying also this type of detection with respect to different configuration of the geometry of observation. Here I report the phase angle with respect to the percentage of detection. You see the blue ones are GDS plus ES, the red one is IS only, and the GDS is green or yellow, something like that. And you can see that, of course, we got a lot of detection when the phase angle is low. But still, even at high phase angle, you still see the GDS staying there. So even when we go to the night side, the GDS appear, while the impact sensor only in the GDS low down quite a lot. Here I'm showing how where they collected. GIADA is able to precisely record when the grain is detected, so also where. And here I report the grain detection. This, you can see the 10, the 20, and the 30 kilometer bound orbits around the comet. And these, you can see that on the part is more dense, the presence of the grains. This is because the most active area, the neck and the upper part of the comet, as Olga showed you before, while rotating, is the active area is pointing upward, and you see that the dust is more numerous in this side of the plot. Here is how it's distributed again along the trajectory of the spacecraft, so where GIADA detected each grain, and this is in another reference frame. This is with the Comet fixed reference frame. And again, you see how it much populated the upper part of the plot. Here, I'm showing you how the speed is varying with respect to mass. As I said, we can measure mass and speed, and so you see that it's going as expected. At low mass show higher velocity, and higher mass they show lower velocity. And looking at this, we also try to see if there was some changing with respect to the orbit. We selected those grains that were collected during the 10 kilometers bound orbit, the 20 and the 30, and higher than 35. And we were, if we were inside the acceleration region, we would have expected like 3 curves getting like separated one to the other. Instead, what we see is that the plots are they plot just in the same curve. So this means that let's say this can suggest that acceleration region should be smaller than 10 kilometers. Okay, so the conclusion. You see, as I said, that the detection was quite early, when the comet was quite far from the sun and the space are quite far from the comet. And GIADA from the 1st of August till mid-December collected about 800 grains. And for about 70 of these grains, the momentum, the mass, the speed, and the cross-section the geometrical cross-section were measured, and the grain densities were constrained. These are, of course, measurements that actually were not performed before then, this in space exploration, so we are quite happy about this. And here I leave you with the acknowledgement of a big team, and also a very important contribution from ESA, RSGS, and of course ERMOC, and project scientists supported by Claudia, and some thank also to NASA because of supporting COAIS in GIADA experiments, and of course a thank also to Angeletta Corradini, who was a GIADA COAI. That's all.
Okay, the paper is now open for questions. Uwe?
You didn't talk about the dust production rate, and you did not talk about the dust-to-gas ratio. Could you comment on those 2 questions, please?
Yes, actually, with a common effort, GIADA and OSIRIS measurements, we calculated the dust to gas ratio, and also using also the data from Rosina and Miro for the gas information. We actually submitted a paper to Scienze, but we are still under evaluation, so this is the reason why I didn't speak about this part of the work. But what we have done till now is the measure of the dust to gas ratio, and also the definition of the size distribution for three mass beams from the GIADA side, and other 3 mass beam from the OSIRIS side.
Any more questions? I actually have a question, which is, in terms of, have you thought about looking at the charging of this dust in terms of how it's distributed around the comet?
Yeah, we are working on this, charging effects on dust together with the RPC team, because in fact what we see is that the dust seems to be quite influenced by the charge of the environment. So we are looking very deeply on this.